So today we'll be doing an old midterm problem from spring 2016. It was their midterm 2, and the problem is as followed. A thin copper wire is sliding on a conducting loop at a velocity u in a spatially uniform magnetic field given by B is equal to 0.02 cosine 500t Tesla into the page as shown in the figure. At t is equal to 0, x is equal to 4 meters, and u is equal to 50 centimeters per second, what is the direction and magnitude of the induced current on the loop? The total equivalent resistance of the loop and wire is equal to 5 ohms. So I just drew it on this paper to make it easier to see. And the question I just read is essentially just asking for the direction and magnitude of the induced current. So to find that, let's write down the equations that we will be using. So we know that flux is simply just equal to B dot dA, and we can use this flux to find the electromotive force, or the voltage, the induced voltage that would drive the induced current. And this is simply just negative d phi, or flux, over dt. And we can use the electromotive force to find the induced current, which is just VEMF over R. So the first thing we're going to do is just find the flux. So flux will just be equal to the integral of B dot dA, and B is given right here. So B would just be 0.02 cosine 500t dotted with dA. So what is our typical element going to be in this case? And the typical element that I'm going to be using is just going to be little strips. And the length right here would simply just be dx, while this length would just be 20 centimeters. So to put that into the formula, I will write 0.2 meters, because 20 centimeters is equal to 0.2 meters, times dx, which is just the area of this little strip. So what will our limits of integration be? Well, since we're going to be taking the integral of this area right here, it will be from 0 to x. 0 to x. So now we just take the integral, which will just be this whole thing times x. So it will just be 0.02 times 0.2 is just going to be 0.004 times cosine 500t times x, from x to 0. And if we plug that in, we just get 0.004 cosine 500t times x also. Now we can use the flux to find the electromotive force, which is just VEMF is just equal to negative d phi over dt. So we simply just plug in what we got here into this formula right here, which will just be negative d over dt times this 0.004 cosine 500t times x. Now, it's I think it's a common mistake, well for me it was, where I just looked at this and saw that the only thing I have to derive is cosine, because the t is in here, but that's not exactly true, because as you think about it, x is a variable that changes with respect to time also, because as this copper wire moves, x is also changing, which means x is also a function of time. So, as you think about it, remember the good old physics days, dx dt is just equal to velocity. And in this case, our velocity is u. But our u is going in the negative x direction, because 0 to x, and it goes from x to 0. So in this case, it's negative u. So, to solve this derivative, we have to use the product rule. And you should remember what the product rule was. It's d over, if we have two functions that are being multiplied, simply just f of x times the derivative of the other function plus f of x prime times g of x. So, taking the derivative of this will simply just give us V EMF will just be equal to negative 0.004, where the negative came from here and here, times cosine 500t times negative u, which is the derivative of x, plus negative 0.004 times negative sine, because the derivative of cosine is negative sine, times 500t times 500 is a chain rule, times x. And this will be our electromotive force, So now that we know what the electromotive force is, or the voltage, we can see the induced current also, which is just V EMF over R. So, plugging in what we have for V EMF, it would just be negative 0.004 times cosine 500t times negative u plus negative 0.004 times negative sine of 500t, sorry this marker is dying, times 500 times t, all over the resistance, which is 5, which was given to us. T. So to simplify this, I induce we know that this is positive and this is also positive, so it's just going to be 0.004 times cosine 500t times u plus 0.004 times sine 500t times 500 times t, all over 5. So now we can just plug in our variables, because we're trying to find the magnitude of the induced current. So at t is equal to 0, we know x is equal to 4 and u is equal to 50 centimeters per second, or simply just 0.5 meters per second. So plugging it in here, we get I induced 0.004 times cosine of 500 times 0, because time is 0, times u, which is 0.5, plus 0.004 times sine 500 times 0 times 500 times t times, actually I wrote this wrong, this was actually x, sorry about that, x times 4, all divided by 5. So once you plug this into your calculator, you're going to get I induced is simply equal to 0.0004 or 0.4 milliamps. But the real question comes, and what is the direction of the induced current? Well, a good way to think about this is, as this bar moves left, which is what it is doing, this area is going to become less and less. So what does that mean? Well, in terms of flux, as you have less area, according to this formula, flux will start becoming less. But we can also make the argument that as this area gets smaller, there will be less magnetic field also, because this area is getting smaller, which also means there will be less flux. So what does that mean? What that means is when the bar is moving, you will get less magnetic field, which also means we will also get less flux. So the induced current, according to Lenz's law, will try to mitigate this loss in flux. So we want the magnetic field, the induced magnetic field, to go in the same direction as the original B field. So how do we get that with a right-hand rule? Well, we can test it out. So let's just say we have a current going this way. Which direction would the magnetic field go in? It will go into the page. So that means the current will be going this way, or clockwise. You can also try the other direction, which will give you a magnetic field that comes out of the page, which is not what we want. So that means the magnetic field, the induced current is going clockwise.